Hello, good morning, KansasFest. I'm excited to talk to you today about GTE, the generic tile engine project for the Apple IIgs. I'll be covering the engine itself, some of its design goals, some implementation details about how it achieves its performance and what its capabilities are. We will be showing a lot of demos during this session, so we'll be fairly light on deep technical details and more about showcasing what the engine's capabilities are. So let's start with an overview of GTE and its goals as a project. So GTE, the generic tile engine, it's meant to be useful for supporting many different kinds of games. It tries to expose similar concepts that were used on the consoles of the Nintendo and Genesis era, so mid to late 80s as a sweet spot, and allow those types of games to be implemented in a fairly straightforward manner on the Apple IIgs, while at the same time trying to take advantage of some of the IIgs's unique capabilities to extend things just a little bit. So the goals of GTE are to be flexible, be featureful, and be, quote, fast enough. So by flexible, we mean minimal restrictions. It really tries to work hard that all of the capabilities that it offers can be used together. So you're not artificially limited to say, I can only use sprites if this other capability is turned on or off. The API really does try to be very orthogonal so that you can mix and match different features together. That's not always the case, but it does try to provide a pretty uniform API. In terms of features, we really try to leverage the IIgs's quirks and throw in a few clever techniques to keep things fast. We'll go into those details in a little bit. The biggest unique part of the Apple IIgs that we leverage is, first of all, of course, the ability to map the stack onto the graphics screen. There's been other KFest presentations in previous years on how that works, and I think quite a bit of discussion and documents out there. So we won't be going over any of that in detail. But the one thing that GT really does leverage is, the Apple IIgs has really good sound capabilities. The graphics are weak, but especially for the era, it could address a lot of memory. 8 megabytes of memory back in 1986, 87 was significantly higher than a lot of machines then. So GTE really does trade memory for speed, and really and it's really not shy about using a lot of memory in a lot of places. So we'll characterize that later, but if you were to develop a full game around GTE, you're probably targeting a machine with like 4 megabytes of RAM is what you would want to use. And then finally, the engine really does strive to be fast enough to be fun. We're not going to have 60 frame per second scrolling sprites over the screen, but we can be fast enough that it's an enjoyable experience, and we can give enough flexibility that that your game can be scaled to meet a particular performance envelope. Before we jump into the core functionality of GTE and how it works under the hood, I wanted to talk a little bit about the development process around the library itself. I do all of the coding in Visual Studio Code using Merlin 32 as an assembler, and I typically run everything under an emulator just for convenience and being able to develop quickly. The content that you're going to see in all of the demos uses the TileD map editor for doing map editing, Paint.net usually for authoring the tile sets, and then I have some custom scripts that are part of GTE that takes care of building those assets and getting them into the final project. So what that can look like is in TileD, we work with standard tile maps. So you can see here, this is going to be the map that we're going to see in our first demo. You can see the tile set off to the side, and we really build pretty basic maps in terms of what TileD offers for capabilities, but it's a very convenient tool. It's very fast to build these levels, and there's other more advanced capabilities that we can use tile these features to expose within the editor rather than having them to do them in code. Once a tile map is built, it gets exported as a JSON file, and then that JSON file is what our tools parse into the code. What that looks like is in Visual Studio Code. We're going to take a quick look at one of the projects here. This is the custom script I was talking about that takes care of converting TileD projects into our GTE code. And what it'll output are files like this. So a little bit of setup code that'll take care of calling the appropriate GTE toolset calls, and then the processed and output tile map in this case. So the tile maps come out, tile sets come out, a few other generated products come out of here as well. So now let's see how this looks when it's actually rendering content on the Apple IIgs itself. So this first demo is very simple. It's going to load in that tile map that we saw before. And here it is, loaded up. We'll set the emulator to standard speed, 2.8 megahertz. I'll be resetting the speed to 2.8 in all these demos so you can have a good idea of how fast GT is working. So we can see this is just our full screen play field. We're scrolling along. We have two counters in the top corners. The first is a frames per second counter, and then the second is just counting the number of 1 second ticks. We're not going to get into the details about them, but these counters on the top are using a feature of GTE called overlays, which are meant to be able to provide fixed position status screens and other kind of overlay information on top of the scrolling playfield. So right now, the frames per second, it's in hexadecimal, so we're getting about 18 or 19 frames per second full screen. That's because this is pretty much the best case scenario. This is a screen entirely populated with PEA instructions, so it's going about as fast as possible. GT does allow us to redefine the screen size even on the fly. There's a bunch of predefined sizes that we can reduce down and see how the performance increases as we reduce the actual size of the screen. So I've gone down here. This is a playfield that is the same size as Rasten, and you can see we're getting now about 25 or 26 frames per second. So it definitely is starting to smooth things out. If we go down even further to something like the Game Boy Color size, we can see now we're actually exceeding 30 frames per second for this size. So pretty good. And that really kind of establishes the baseline for GTE's performance. So that showed the basic functionality of GTE, but it can do much more. As we add more features to the playfield, we will get slowed down, but one of the major design goals of GTE is that we try to only do the necessary work so that users of the tool can be selective on the features that are used in order to balance their performance against visual effects. There can be four major ways that tiles can be rendered in GTE, and these are marked by the purple circles on the slide here. They can be solid blocks that's shown at the bottom here. That's what the previous map was. It was 100% solid. We can also have dynamic tiles shown on the left here. Dynamic tiles can be updated and share a data source. So updating one tile will be reflected in many tiles on the screen. We can have a secondary background tile shown at the top, which is in a background layer behind the primary background. And then we have tiles where there's overlap. It's mixed foreground and background content. So let's talk about how each of these major modes work and see an example of each of them. Let's talk about dynamic tiles first. Dynamic tiles read data from a direct page location and push it onto the stack. They're set up in a way that multiple dynamic tiles on the screen will read their data from the same memory location. So if that memory location is updated once, that change is reflected in all of the on-screen tiles. This is implemented by using a direct indexed instruction to load the data and then pushing it onto the stack. We use this sequence of 2 instructions because they are exactly 3 bytes long and match the 3 bytes that a PEA instruction takes up as well. The X register is set at the beginning of each line, and it is fixed for that line. However, each line points to a different direct page offset. GTE uses a total of 8 pages of bank 0 memory, 1 page for each horizontal line of the target tiles, and can support up to 32 dynamic tile slots. Okay, let's see dynamic tiles in action. Here we can see the same map that we started with on the first demo, but we've added many dynamic tiles to the map, and we were animating them at 4 frames per second. Notice that the animation speed is independent of the frames per second. If I increase the emulator speed, the animation remains consistent. These animations are being driven by a GTE timer, which provides 1/60th second tick resolution in order to drive animations in a way that is independent of the machine speed. If we reduce the size of the playfield, as we did before, you can see again the frames per second increases, but the dynamic tile animation remains consistent. Dynamic tiles can be used in another way as well. Here we have a map from the NES game Metal Storm, and if we scroll to the right, increase the speed to go a little bit faster, we come to this area where we can see a parallax effect in the background. This is actually still using 1 layer, but we're cleverly using dynamic tiles in order to simulate a parallax effect on this level. Let's take a look at the tiled data for this to see what's going on. If I switch to the Metal Storm tile set, you can see here all of my repeated tiles. And notice that the tiles here, which are the primary tile IDs, are marked as animated tile sets. This tells GTE that these tiles should be allocated within the dynamic tile memory. So we just saw how dynamic tiles can provide a pseudo parallax effect, which is nice, but we'd like to do better. So let's talk about supporting a second full screen layer. There's a lot of reasons for it, but the way GTE implements this is that we allocate a second background layer in a high bank of memory, and then use the data bank register to reference that data from within the blitter. We use a indirect indexed instruction to load a data byte and then push it onto the stack. The way that the data is updated is we need to have the ability to independently scroll the second background in relation to our primary background. The way that works is that when the background layer, the secondary background layer, needs to be scrolled horizontally, the values on the direct page are updated. We only need to update 80 values on the direct page, even for full screen scrolling. Similarly, when vertical scrolling needs to be changed, we go through and patch out a new address for the Y register on each line. So again, for full screens, this would take a maximum of 200 writes. Let's take a look at the full screen background in action using this technique right here. So in this demo, we've taken a level from Super Mario World. The code field is using either PEA instructions or the indirect index instructions to get data from the second layer. As you can see, we do have two layers. And as we scroll along, they are moving independent of each other, giving us a true parallax. However, there's lots of jaggies around these diagonal lines because right now we're limited to only 16-bit writes. A 16-bit value has to either be wholly in the foreground or totally in the background. And then there's no way to blend them, and it really, in my opinion, doesn't look very good. So the problem is that in only 3 bytes of code, there's no way to do a mask between the foreground and the background. And this limitation was really one of the main reasons why I put this project down so many years ago, because I didn't have a solution. But now we do, and we'll see how that works. So when the foreground does not have a fully transparent word, we use what GTE calls snippets, which are small areas of code that have a one-to-one mapping to each word of each line of the code field. This is actually really similar to the technique that Oliver Schmidt talked about with his audio decoding, where there's a lot of specialized routines, and just by knowing which routine you're in, you know where you have to go next. So there's no subroutines here. Everything jumps to an absolute address, and because it came from a unique location, it can always jump back to the next instruction in the code field. So what do those snippets look like? We have 32 bytes of memory to work with, so it's plenty of space to do a standard load, mask, or data in, and then push the data onto the stack, and then finally jump to the next word in the code sequence. There's obviously a lot of complexities and subtleties about how this is actually implemented, but let's take a look at how it looks in practice. So we can see here immediately it looks much better than what we saw before. So here we have per pixel, parallax scrolling, everything is masked appropriately, and everything looks visually very good. So now we've seen all the different ways that tile data can be rendered onto the graphics screen. So now the image that we looked at originally makes a lot more sense. Each of the different tiles are rendered with a different 3-byte code sequence. The mixed tiles, which require more than 3 bytes of code to implement, use a jump instruction to jump to the special snippet areas in order to have a more complex code sequence in order to do their work. These 4 different types of tile renderers encompass pretty much all of the different ways that GTE can get tile data onto the screen, and wraps up how the backgrounds are implemented. So let's take a look now at how sprites work in GTE. Sprites are very difficult to do well in a general way. They are really inherently slow to implement, and to make them fast means sacrificing the generic part of GTE. So currently the way sprites work is we do not use compiled sprites. All sprites are using small bitmaps, and they are rendered by copying data onto the screen. What GTE does do is it splits up the sprite processing into 2 different parts. First, when a sprite is defined, a sprite stamp is created. These are pre-rendered sprites with the different horizontal and vertical flipping bits defined. Then when a sprite is drawn to the screen, the way it works is the sprite's intersection with the different tiles is calculated, so we know which tiles need to be updated with sprite data. The sprite's relative position within those tiles is then used to determine the address offset within the sprite stamp. And then finally, the data from the tile set is combined with the data from the sprite stamp memory to create a pseudo tile, which is then rendered as if it were a regular tile. The advantage of this is we get clipping for free because the sprites are rendered into the code field, not onto the screen directly. We also get the ability to apply some effects because we're dynamically blending the sprites with the tiles before they get written out to the screen. And also, we don't have to worry about flicker because only the data as it will appear in the final form is ever written to the graphic screen. So we don't have to play around with any sort of shadowing. So now let's take a look at how sprites look on our demo levels. So here we have our first level, except now we have a sprite in place. As you can see, our frames per second is still maintained fairly well. As the sprite goes along, we have a basic walk animation, and this is implemented by switching out the sprite stamp that's applied to a given sprite on different frames. So there's only one sprite, but then we're cycling through different stamps in order to provide the animation. I also wanted to call out that GTE is written to be very interrupt friendly, so tools like NTP are able to work just fine. So here's a mod that I converted yesterday and brought over, and as you can hear, it plays just fine and has a fairly minimal impact on the frames per second as we're playing along. Also, I mentioned that having the sprite stamp and the tiles being generated on the fly lets us do some special effects. So here, I borrowed some fence graphics from the Super Mario World tile set, and I can walk in front of them. But the tiles in GTE also have a flag that marks them as high priority or not. And high priority tiles render in front of sprites. So again, we sort of have this pseudo layer effect going on without needing to implement a full second background layer. And this is done at the tile level, so all sprites would be rendered behind this particular graphic. Now that said, the priority bit for the tile store is a dynamic property. So whether or not sprites render in front of or behind a given tile can be changed on the fly as the map is being drawn. With the time that we have left, I have a couple more demos that we're going to just rapid fire through to demonstrate some advanced capabilities of GTE. So this demo right here, you may not have noticed in the first example, but the background has the same 1 byte scrolling limitation as the foreground. However, this is an example where we have an alternate background layer, and as you can see as we scroll along, the background actually has per pixel scrolling going on. So for every step that the foreground takes, the background also moves, but it moves at half the speed. This flicker right here is actually the boundary. There's a boundary effect when I'm flipping the different backgrounds. But the way this is implemented is we use a second data bank and then dynamically change the data bank register depending on what the address offset is. And so if the graphics are created more carefully to avoid this kind of glitch, then you can have an even smoother second background than you do with the normal parallax scrolling. The next demo shows how we can do scanline effects using GTE. So because all of the screen is rendered line by line and we have independent data being set up for each row, the X registers and the Y registers, we can change them on the fly to provide offsets and also animate those offsets. So for the exact same cost that we normally would have in rendering the background, we can apply these kinds of animated effects. And finally, you may have noticed in the description that I gave about how sprites work that essentially sprites use a dirty tile type approach. Well, what happens if we just use those dirty tiles and draw them directly to the graphics screen rather than into the code field and then execute the code field. In that case, we can achieve 60 frame per second updates with multiple sprites on the screen. In this case, the background is drawn once, and the tiles that are dirtied are the only thing being updated on the screen. We still preserve some things like tile priorities, so the sprites can still go behind foreground elements, and we can dynamically switch between dirty updates and full screen updates in order to have the kind of page-based scrolling effect that a lot of games have, and then maintaining near 30 frame per second performance for the screen that you're on. And then finally, we can do interesting things with our background. So loading the background where we use the index indirect instruction, that is essentially doing an addition of the value on the direct page and then combining it with the Y register, loading data, and then storing it. Well, one interesting thing that you can do is rotation is actually something that can be decomposed as the sum of two independent functions. So with a very clever set of table values, we can bring in a background and rotate it at the exact same speed that we would be doing normal parallax scrolling anyway. And because these are just table-based values, we can even do things like increase the scale of the background and decrease the scale of the background as well. This is a very recent addition to GTE, and it still has some work to be done in order to make it a more robust feature, but we're definitely looking to continue to push GTE in the direction of supporting more and more of these kinds of advanced effects where it makes sense. And with that, that concludes the presentation on GTE. Thank you all very much, and I look forward to answering all of your questions. All right, answer, there we go. So there was a question of whether GTE supported higher resolutions of the second sight card. The answer is unfortunately not. Everything in GTE is based around the built-in graphics modes on the 2GS, so super high res modes only, and obviously it targets 320 mode right now rather than 640.
Hello there, this is Dave Slaughter at Corcoran Hall. Just wanted to say, as a fellow developer, this is absolutely amazing. Thank you very much.
Oh, thank you. Appreciate the kind words. I'm glad you enjoyed it.
Okay, any other questions?
Oh, there we go. Yep, I see one here on a thing. So one question was whether there's support for collision detection. The answer is kind of. Right now, the engine tracks sprites on a per tile basis, so that information is being tracked internally, but I haven't exposed it yet outside, mainly because I'm not sure whether the granularity of detecting collisions on a tile level is particularly useful or not. I know just from reading various sources, like a lot of Nintendo games, they have their own collision detection methods and they don't really rely on any sort of a generic built-in collision detection, but it's something that could easily be exposed if it's useful. And a question from also on Discord, is the tile size variable? No, actually the first iterations of GTE, I looked at making it variable, so like 8x8 and 16x16 tiles, but that just ended up blowing up the number of combinations that the engine has to support. So I've settled on just a consistent 8x8 tile representation for all tiles within the engine. And there was a question on how much accelerators help in terms of frame rate. They help a bit because there's so much writing to the graphics screen where things get throttled to 1 megahertz. Having a zip in there, you get probably 40 to 50% of a frame rate increase over stock. So it definitely helps, but it's not like you're going to get 3 times the frame rate by having an accelerator in there.